All right. Good evening. Tonight, I thought we would open up our new geology kits that we have, kind of see what all's inside. I think I have a general idea, but thought it would be fun to share with the internet here. We've got our calculator. We don't need it though. We'll use our pencil, and then we'll have this for put that right there for scale, so you guys can see. These are centimeters across the top here, so for scale, just for reference. All right. Nice little box. It's fairly thick here on the side, so it's got some good height to it. Let's open this bad boy up. See what all we got here. All right. We have some acid. This is 1 molar hydrochloric acid, so not like the world's most dangerous or most powerful acid by any means, but it could still cause, I don't know, a little bit of a burn or a little bit of a sting possibly. Have some acid right there. We've got our, this is from Ward's, but this is our rock and mineral test kit here. So this has a variety of tools that we use to do our analysis and collect data with. I'm always kind of jealous. Chemistry and physics, they get like computer stations with all kinds of like fancy equipment, and then this is what I get. I have a white ceramic plate here. We use this to test the streak of minerals. What else do we have in here? Sometimes they give us a black one. Sometimes there's a black ceramic plate, but we only have a white one. I don't know if I have a black one with me here today. No. We have a glass plate, so this is used to test for hardness. The hardness of glass is right around 5.5 on the Mohs hardness scale, so we can use our glass plate to test for that. We have a piece of copper, a copper strip. Um, Usually I just use a penny because a penny literally costs 1 cent. This probably costs more than a cent, especially if this is real copper. We have a nail. We also use nails for testing our hardness using the Mohs hardness scale. Nail's hardness is about 4.5 out of 10 on the hardness scale. And then we have a magnet. Right? We can see how it attracts the nail. There is a mineral or two that are magnetic, so we can test magnetism with our magnet. And then we have a very simple, very nice, it's kind of simple little magnifying glass here, so you can get a little more detail on some of the minerals, some of the crystals or whatnot. Lick the rocks and tell me which is the tastiest. Green Owl says so. We'll lick some of them at least. I don't think I'm gonna lick all of them. Some of them you don't want to lick because yeah, they have sulfur and lead and stuff in them, so we don't want to be overly exposing ourselves to that. All right. I'll pretend it's my class. If you guys ever do rock and mineral testing, a couple of quick safety tips here, kind of safety reminders here. But overall, I mean, not a lot of safety concerns compared to, like, again, a chemistry or biology kind of lab or class. But whenever you're testing like hardness using the glass plate, you always want to keep the glass plate on like the flat table surface and then push into it. You don't want to scratch. You don't want to put it in your hand and then apply pressure because sometimes these get scratched up from other students or whatever. And then if you scratch it, it can shatter in your hand and ouch, right? That would hurt. Same thing applies to our streak plate. So we want to always keep those on the table when we use them. And then it's important too to wash your hands after you've been handling these. Especially, I'm never going to be pregnant, right? I'm not. I don't have the materials. I don't have the parts for that, right? But especially susceptible if you're like pregnant or if you want to become pregnant or whatever. Some of these things can be toxic and can cause issues. If you're an adult, it's just wash your hands. It's fine. But I've had female students and I've given them gloves, out of abundance of caution. So same applies there. All right. But let's see. We've got two boxes in here. We've got a smaller kind of red box here, and then we've got a larger red box here. This one is completely sealed still. You can see the shrink wrap is still on it. So I have not Not open this one up at all. I think these are the rocks. Let's see here. Instructor's Rock Collection. Yep, that's us. All right, let's close this up. And we'll start with the smaller of the two boxes. And then we'll move on to the bigger one here. Let's put this on the floor. So our smaller of our two boxes. Let's get our knife out. We can crack this mamma jamma open here. I was doing plate tectonics the other day, so we're talking about rates. Let's pull out our knife. And okay. Let's put our testing supplies up here. We don't need to test everything, but it's nice to know that we have them. Put all that there. All right, you guys ready? Oh. Nope. Look at that. They gave us some more testing supplies actually in the mineral kit. So we have an even smaller magnifying glass. We have an even smaller ceramic plate. And we have an even smaller nail. All right, let's put these to the side. Mineral study kit. The common minerals in this collection will have distinguishing characteristics which identify them. Yes. We do use our 5 senses. Yes, we do that. Okay. Okay. Well, look at these. Look at this. This is awesome. Look at this little kit. Look at this. Isn't this awesome? This is so cool. I love this stuff. You could say I love this schist. Schist is a metamorphic rock. Number 1. This is kind of cool looking. Number 1, this is fluorite right here. So fluorite, this is not the best sample. I mean, these are for the kiddos. They don't give us the expensive, super fancy ones, in the kit boxes here, unfortunately. But fluorite is kind of a cool, unique mineral. Fluorite's chemical formula is Ca. I think it's CaF2 or C2F, something like that. I forget my valence electron orderings. But calcium and fluorine are in fluoride, or are in fluorite, and fluorite has fluorine in it, and fluorine is used in toothpaste, fluoride in the toothpaste. Don't brush your teeth with this. Samples of this will sometimes show what we call, what is it? It's a cleavage, but it is a tetrahedral cleavage, so it's got 8 sides to it, so they can form octahedrons, right? Not the best crystal sample here, but this is our fluorite right here. Fluorite, though, it does come in a wide range of colors. So this has got a little bit of greenish kind of hue to it. But you'll sometimes see some with like purple in them. Hopefully you guys can see that. I want the light on, but not maybe directly. But there's a bit of a greenish kind of hint and a hue to it. I don't know if I have any more fluorite nearby. Let me see here. What's this box have? We got boxes of rocks in here. Such is life. No. Do we not have fluoride? What about down here? Just want to show you guys I think it's this one. Just wanted to show you guys maybe a better sample, a better version of what it looks like. Where's our fluoride? Oh, here we go. So here's another version of fluoride. You can see it's much greener, so much more vibrant color here. But then, yeah, if anyone plays like Dungeons and Dragons, for example, fluoride will naturally break into crystals that look like this. This is our D8 here. This is our octahedron crystal right here. Yeah, looks like a D8 you would roll, right, in D&D. All right, but they naturally break like this. That's kind of cool. So when we look at the crystal shape, there are 2 things. There is habit and there is cleavage. So crystals have a habit of growing a certain way, we kind of say. They have a habit of how they grow. So when we talk about crystal habit, we're talking about the naturally occurring crystal faces and crystal planes. When we're talking about cleavage, we're talking about how minerals break. And so minerals will have planes of weakness within their crystal structure, within their crystal lattice. And when you whack them, they will break preferentially along those crystal planes. And so fluorite will not grow like this, it will break like this. So it has what we call the 4 planes of cleavage. When we talk about planes of cleavage, we're talking about, think about your geometry, right? So this side is the same as this side. So where my fingers are, these are the same plane. This would be the same plane, and then there's two more. So this one has 4 planes of cleavage. We have some minerals with 1 plane of cleavage. They almost look like paper. Some minerals will have 2 planes of cleavage. They look kind of like a prism. Minerals with 3 planes of cleavage, they can look like parallelograms, or they can look like cubes. And then fluorite is really the only common one, at least, that has 4. There might be more out there. There's like 5,000 minerals out there, but fluorite, very common mineral, and it's really the only common one with 4. Okay, but that's a cool one to start off with. I personally like fluorite quite a bit. It is the Illinois state mineral, so a lot of fluorite came out of Illinois back in the day. Not so much these days. Most of it comes out of Brazil. All right, next one. This is going to be one of our feldspars. This is the feldspar right here, number 2. This is the official version is microcline. I call it orthoclase feldspar. Try and keep it a little bit simpler, but microcline orthoclase feldspar. Feldspar is one of the silicate minerals, so it has silicon and oxygen as the anion, the kind of the ending half. There's usually inside of feldspars you can have aluminum, you can have sodium, you can have calcium inside of them. But the silicates in general, the silicate group, things with silicon and oxygen binded in them, are the most common of all the minerals, the silicates. The reason for that is that the Earth's crust, the 2 most common elements in the Earth's crust are silicon and oxygen. The 2 of those make up like 77% of the Earth's crust totally. And the reason that they're so common in the Earth's crust is because they have a lower density. So when the planet was forming, it was a rather homogeneous mixture of material. And then as it heated up and things started to melt, we have gravitational separation due to density. Heavier things basically sank to the inside of the Earth, and lighter things floated to the surface. So we have lots of like aluminum and silicon and oxygen in our crust, whereas most of the iron inside the Earth is inside the deep part of the Earth. It's kind of crazy. If you look at the entire planet, the most common thing is actually iron. But if you look at just the crust, it's the 4th most common thing, because a lot of that iron got sent down deep inside the Earth to make the Earth's core. But this is one of our feldspars. I don't know if there's 2 in this box yet. I haven't gotten that far, but we have at least 1 in this box. Feldspar also, I think, don't quote my German here, but I believe it gets its name from like Feldspar, which is like German for like field rock, like field sample. Feldspar is the most common mineral. Again, it makes sense. It comes from the most common mineral group, right? So feldspar is by far the most common mineral on the planet. And it's not always common where you live, it just kind of depends, but overall it is the most commonly found, most common, most plentiful mineral out there. Let's go to the chat here. If I'm not supposed to eat them, why does the box look like one that they put life is like a box of minerals. You never know what you're going to get, Green Owl. How do I walk into this guy talking about cleavage? I just do be like that. That right there is crack rock cocaine. I mean, you see what you want to see. I wouldn't snort it. Probably wouldn't end very well. Sitting here eating a Twizzler, wishing it was some rocks. I know, right? The rocks are just delicious. Imagine playing D&D. Yeah, D&D is for dorks. I agree. This New Jersey Wi-Fi keeps buffering, Aaronite. I'm sick. You would think of all places New Jersey would have decent Wi-Fi, but Twitch is having issues tonight. Oh, okay. Feldspar is number 1 in my heart. Is feldspar common in NYC? That's a great question. I don't have the answer to that for sure. New York City was bulldozed by glaciers during the last glaciation. I know there are some rocks in Central Park that are like igneous boulders that were dropped there by glaciers. So you probably could find some feldspar in some of those boulders in Central Park. I don't know the amount, the relative abundance, but yeah, you could definitely find some in New York City. You can tell this one's not from New York City because it has good taste in pizza. So I'm not from New York. So, but mineral number 3 here. Number 3, this is kind of cool. kind of red and crusty. This is hematite right here. Hematite is FeO2, I think, Fe2O3, something like that. Basically, it's just iron and oxygen, and so if you're familiar with iron and oxygen, that's going to be rust, right? Essentially, right? If you have an old car, if you have old tools or whatever, rust, right? And so yeah, we have, this is the mineral version of rust right here. Some hematite is slightly magnetic. I don't think ours is going to be, but let's see here. Is there any attraction? No, there's no attraction there, just like me and my ex. All right, no attraction here. But hematite right here, yeah, iron and oxygen. A couple cool things about hematite. We suspect that very, very long ago, back about 2 billion years ago, creatures first figured out photosynthesis. And when they did, they released a tremendous amount of oxygen into the Earth's oceans. That oxygen then reacted to the dissolved iron that was in the oceans, and it formed a rust like this. And hematite rust is relatively insoluble, so it came out of the water solution and it deposited. So we have what are called banded iron formation, these really thick layers of hematite and other iron-rich minerals that we can find. But they're all about 2 billion years old, and it correlates to when we think life figured out photosynthesis and drastically changed the chemistry of the oceans. So that's kind of a cool thing with hematite. Usually there are two versions of hematite, like in our other geology, in the boxes that we use in our in-person classes. We have both metallic and non-metallic hematite. The difference being that let's see here. I don't want to damage the new one. The lab assistant might get mad at me, but I have a regular streak plate here, another one that I've been using. We're going to use our safety, right? We're going to put it on the table. But the cool thing about hematite is that it always produces a red-brown streak, so it doesn't matter the color, it doesn't matter the luster. It's always going to have that red-brown pretty streak to it. That's one way I tell the students you can easily identify hematite, even if you're not really sure on the color or the luster. Luster, I didn't mention it, but luster is how the minerals reflect light back. And so in Intro to Geology, we kind of keep it simple. We either say it's metallic or is it non-metallic. And so the first three have all been non-metallic. Number 4, which we'll get to in a second, but number 4 has more of a metallic luster. Hopefully you guys can see that. I maybe need some better lighting in here, but it does kind of sparkle a little bit. Let's jump back to the chat. Dude, I love laying down on the rocks in Central Park like a cat. Interesting. All right. But that's hematite right here. Hematite is also commonly found in sandstone, and it will often stain the sandstone red. So maybe you've seen like picture rocks or the wave, for example, in Arizona. The wave is layers of sandstone with varying amounts of hematite, and it produces really cool like pattern, really cool striped colors. I think Onion's been to my house, and she's maybe seen my artwork, and I have the wave on the wall in the living room here. But anyways, number four is a metallic mineral. It's our first metallic one in the box, and it kind of has a pretty gold color. But we would never give the students gold; they would take it, and they would never come back. This is fool's gold right here. This is iron pyrite, or just pyrite. Pyrite's chemical formula is, I think it's Fe2S, I think. So iron and sulfur make up our pyrite. The ancient Greeks thought there would be a way to convert this into gold. Not the case, because there is no gold, no elemental gold in here. It just kind of has the color and appearance of gold. The way you can tell pyrite apart from gold, pyrite is relatively hard. It can usually scratch glass, whereas gold is very soft. Pure 24 karat gold is very, very soft, very, very malleable. You can like bend it, you can bite it. Yeah. This is our pyrite here. Kind of cool. We can find pyrite in places like near hot springs and whatnot, near geothermal areas. Also, for some of the Earth's history with life, they did chemosynthesis. So instead of using light to make energy, they used chemicals, and sometimes their waste products were sulfur-based. And so you could find this sometimes associated with fossil deposits. Sometimes from before like photosynthesis was a thing. The temporary art, no. The legitimate art that has been fully approved is in the living room, or the dining room, I should say. Yeah, I don't want to chew on this. This would chewing on pyrite would definitely mess up your teeth. The miners used to do that, though. They would put it in their mouth and see if they could bite it, and if they could bite it, they knew it was real gold. And if they broke their tooth, maybe they knew it was pyrite. Number 5, a classic, everyone's classic mineral here. You can find this in every gift shop, for every cave, and every museum. You can find this at a lot of places. This is actually the second most common mineral. We said that feldspar, number 2, was the most common, but this is the second most common. This is quartz right here. I could talk about quartz all day. But this is milky quartz. Quartz comes in a variety of colors. You can have purple quartz, which is amethyst. You can have like an orangey red, yellowy kind of quartz, that's citrine. You can have black quartz, that's smoky quartz. You can have clear quartz, sometimes called crystal quartz. If it's pink, it's called rosy quartz. It comes in a wide range of colors. The colors are from different impurities, so different elements getting inside the crystal lattice, and that changes it. I think amethyst, don't quote me, but I think amethyst is titanium inside the crystal structure. I don't remember exactly. But yeah, different elements get inside there and produce different colors. Quartz is literally just silicon and oxygen, believe it or not. SiO2 is the chemical formula for quartz. It's one of our silicate minerals, making it very common, just like our feldspar, right? Silicon and oxygen, very, very common. What else can I say about quartz? They use quartz in a lot of watches to keep track of time. When you apply electrical current to quartz, it vibrates at a known frequency, so it's really, really good at keeping time. What's kind of crazy is you can go to Walmart, you can go to Target, you can buy a cheap quartz watch, and it'll keep time better than every Rolex ever, right? So your $20 watch from Target is better than a $20,000 Rolex in terms of keeping track of time. Quartz too is of interest in the semiconductor industry because the main things that come out of quartz are silicon and oxygen. So there are very, very pure quartz sands. I think they're in either Tennessee or Kentucky, but they do a lot of quartz sand mining there, and they use that sand. Then they purify it, they melt it, and they extract the silicon, and they use that for computer chips. And it has to be super, super pure, right? Because those computer chips are down to 5 nanometers for the little circuits, the little gates or whatever. So you have to use very, very pure starting material for computer chips nowadays. And so we use quartz for computers. So we literally program minerals to think in some cases, right? Let's go back to the chat. Rose quartz is my favorite. Only raccoons are pure enough to deserve protection. All right, Rolex. Yeah, Rolexes are nice watches. If somebody wants to give me one, I wouldn't be opposed. But it's not going to be as good of a timekeeper usually compared to a relatively cheap quartz watch. All right, number 6 here. Number 6. This got to be calcite. Yeah. So this is calcite right here. Calcite's kind of unique. We talked about cleavage when we talked about fluorite, right? So a good sample of fluorite will have the 4 planes of cleavage. Calcite, a good sample, will have 3 planes of cleavage. And what else is cool about calcite is the 3 planes are not at 90 degrees. And so if you look here, and I put my fingers on it, you can see that it doesn't form a 90-degree angle, right? You can see if it was 90 degrees, it'd be more like this. My finger lies flush against it like that, right? And so this does not have cleavage at 90 degrees. It's got, I think it's 105, 120, something like that. So that's one thing that's unique about calcite is the fact that the cleavage planes are not 90-degree angles. Calcite is often confused with halite, but there are a couple of different ways you can tell calcite apart from halite. Calcite is going to be harder, so your fingernail won't be able to scratch calcite. Calcite has 3 planes not at 90, and then let's see if we can pull this off. I don't know how good these samples are. It's my first time working with them, but calcite will hopefully, fingers crossed here, everyone. Let's see what we got. Calcite will hopefully fizz when we put acid on it. Yeah, you can see there are some. Hopefully you can see it. If I take the light away, maybe. Chat, are we cooked? What if I turn this light off? You can see there are some bubbles in the. It's kind of hard to show here. They're pretty small, but you pour a little bit of the acid. The acid is clear. Let me see if we can do it again without the light. Maybe put some over here. Yeah, you can't really see that, unfortunately. Oh, you can see it's. Maybe you can hear it if I put it next to the microphone. Probably not. But calcite, it does react when you put acid on it. So that's why our mineral kits have the acid in the first place, is to test and see if the sample is a carbonate or not. Chemical formula for calcite is CaCO3. Calcite is one of the most common non-silicate minerals. A lot of animals will make their shells out of calcium carbonate they extract from the seawater. And so calcite forms our limestone. We'll hopefully see limestone in the rock box when we get to it. But calcite's a kind of a cool mineral. It fizzes, right? It's kind of got a unique property. It responds and reacts to acid here. I bet Erudite doesn't know who this is. I don't know who everyone. It's fine. Sand never gave consent. Yeah, dressing that calcite in some delicious acid sauce. That's right. What would I do if I was sold calcite and it didn't fizz? Man, so that's a good question. There is another mineral actually that looks a lot like calcite. It's called dolomite, and it's Mg, Ca CaCO3. So it has magnesium in its chemical formula in place of some of the calcium, and so dolomite doesn't fizz. Dolomite fizzes very very weakly compared to calcite. So if I was sold it, I think I would correct them and tell them, hey, it's dolomite. Go get me real calcite though. The way you can check the difference between dolomite and calcite is what you'd want to do is you take your nail, you'd scratch up the surface, and then you put acid on it, and then if you see a more of a fizz, then you know it is dolomite. So that's how you tell the difference between calcite and dolomite. Put that one back. Number 7. This one, man, some of these samples are rough, guys. I feel bad for some of the students, but this is another version of quartz. This is going to be chalcedony right here. This is what we call a microcrystalline variety of quartz. So it's made of a bunch of small little crystals that are stuck together. So we don't have some of the nice kind of sparkliness to the other quartz that we have. But these are both versions of quartz. One way we can get like chalcedony, there's other things that are very similar, like chert, flint, jasper are all microcrystalline varieties of quartz. One way you can get those kind of things forming, there are sea creatures that live in the ocean like plankton, and a lot of them make their shells out of calcite, right? That makes our limestone, but there are some animals that make their shells out of silica, silicon and oxygen, and when they pile up and die, you can get like things like chalcedony, you can get things like chert and stuff forming then as a result. So it's basically just another version of quartz, but it kind of shows some of the differences, sort of some of the kind of curiosities of it. All right, number 8. If I can get it out of this box. Dolomite was a tank. Drama in the geology community. Budget costs. All our rocks are yeah. It almost feels like it. I when the department lets me, I take the department credit card and I go to the rock and mineral shows, and then I can actually see and buy like physically. Oh, that's the sample I want, right? And so that's nice because you get what you actually want. When you order online, sometimes the pictures they show you are not indicative of what you'll get sometimes. There are better versions of number 7 out there for sure. We have samples in some of the boxes that have like bands and stripes in them, and that makes them pop a lot more, and it's a little bit easier for the students to identify. Number 8, though, we have another not the best sample, but hopefully you guys can see it's got a bit, kind of a metallic-y kind of color to it, metallic-y kind of look. Here, what if I lower the camera, maybe kind of does like a pseudo zoom in by physically lowering it a little bit. But you can see it's a bit more metallic, right? A bit more sparkly. Number 8 is magnetite, and the key property, hopefully you could figure it out, magnetite should be, there it is, right? Magnetite is magnetic, right? What an easy way to remember that one. All right. Magnetite is magnetic. It's just iron and oxygen, so it's kind of similar to number 3 we saw, which was hematite, right? Kind of similar to our hematite. Hematite is iron and oxygen as well. So what's the diff? Why is that? Again, I'm not a chemist here, but iron can have different amounts of valence electrons. I think it can either be +2 or +3. I believe this one is the +2 valence, and this one is the +3 valence. And so the different flavors essentially of iron can determine its properties here. And so they're both iron and oxygen. Those are the two elements, but one basically has been arrested and one has not and is magnetic. All right, so magnetite is magnetic here. Magnetite sounds like a Pokemon. Isn't it Magnemite or something? Magnetron or something was one of them or something like that when like 3 of them joined together. Number 9 here. This is actually this is an okay sample. Number 9 though, this one it's coming off my hands. It's white and powdery. But number 9 should be very soft. I'll double check. Yeah, so my fingernail, hopefully you guys can see that. I don't want to scratch it up too much, but my fingernail actually scratches number 9. So it's very, very soft. Your fingernails are about 2.5 on the Mohs hardness scale. And so, if your fingernail scratches, it's got to be less than 2.5. This is actually going to be gypsum. Gypsum is what? What is gypsum? It's a sulfide. I forget the first part. It's a sulfide. It's either calcium. It might be calcium sulfide. I can't remember. Apologies. I'm not a chemist. But this is gypsum right here. A very, very soft mineral. They use this to make like drywall, to make like plaster with. Some of the gypsum will be kind of more transparent, be more translucent here. But the easiest way to kind of identify it is the fact that it scratches super easily. Some gypsum samples will have better cleavage than this one. Sometimes you can see one nice plane of cleavage. This one, not so much. All right. Number 10. This one's a pretty easy one. This is one of the few minerals that you can identify based on color. I always tell my students you shouldn't, just like you shouldn't judge a person by their color, you shouldn't judge a mineral by their color. But this is one of the few cases where you can. Really, it's the only yellow one that we see. Oh, that's interesting. The box says number 10 should have been talc. It says talc is no longer available. So talc is often, if I had to guess, talc is often found with asbestos minerals. So you don't want to be breathing those in ideally. So they swapped the talc out for number 10 here. Number 10 is yellow. It is sulfur, right? So sulfur, this is actually an element. So there's no chemical really formula. It's just pure sulfur. Pure S right here is the chemical formula here. But sulfur stinks. If you rub it and powder it, it produces a very, very stinky smell. Sulfur is what you smell like in rotten eggs and like bad body odors. So that's what we have here. We have pure elemental sulfur right here. Sulfur was the name of my I think it was my Warlock alt when I played World of Warcraft back in the day. Here's a fun one. Number 11. All right, number 11. Kind of looks transparent, kind of translucent, right? Hopefully you guys can kind of see that. And you can kind of see there's almost like a stair-step kind of patterning kind of going on. If you guys can kind of see that in the profile view here. It's very it's like goes like straight and it like cuts down, and it goes straight and it like cuts down again. We're seeing that here. A good sample of this will actually have 3 planes of cleavage, and it makes nice, perfect little cubes. And this is one of the few minerals you can actually safely eat. In fact, you've probably eaten some of this mineral today already. Number 11 is NaCl, or more commonly known as salt. In the geology world, we call it halite. All right, so halite is our mineral here, NaCl. This is one of the few that you can like. Oh, that's pure salt. Oh God, that's literally the saltiest thing you can taste. Besides having to listen to people gripe about their loot in World of Warcraft. But yeah, this is pure salt right here. Pure salt is harder than your fingernails. So that's one way you can distinguish it. A lot of times gypsum will be kind of clear, kind of transparent, translucent like this, but salt is actually a little bit harder than pure gypsum. And so that and the fact that you can taste it and it tastes like salt gives it away. I never make my students lick the rocks, lick the minerals, because they've been touching all kinds of nasty things beforehand. So now there's sulfur and crap on this. I even tell them on the test if they ask. I'm like, hey, you can ask me one question in the test, and so they ask. I ask every sample, is this salty? Is this salty? And eventually I tell them yes, because there's usually 1 or 2 that are salty. But yeah, if you're in the field and you want to identify, lick it, and if it tastes like salt, that's because it is. Let's go back to the chat here. Looks like someone does not appreciate talc. Should be called dozite. Sulfur was that's right. That's right. Gave this guy a tish. Yep. You want to eat that mineral. I'm the crunching cat with mineral 11. Strong. It's very salty. I mean, it's not going to find anything more pure than that. I guess I have a little salt story I can tell you guys. My mom was a teacher up in Chicago, and so I would go into the classroom and I'd bring rocks and minerals, and I'd talk to the kids about like geology for like career day. They were always very excited, you know. Oh yeah, this is great, you know. Oh, I love your rocks. And then one time, the kids they came in from recess, and they came in and they brought me diamonds that they had found on the playground. And I was like, wait, what? Diamonds on the playground? Like, what? How rich is this school, right? And turns out that it had just snowed the night before, and so they had sprinkled a mineral on the ground, and the kids had picked them up thinking they were diamonds, but the cubes that they brought me were salt cubes, and so I washed one of them off and I licked it, and they didn't believe me, so then we washed off some more, and then I had second graders licking salt all day, and I guess it caused a disturbance later on, but hey, they learned, right? They learned how to identify salt, all right? Moving on to number 12. All right, this might date me, but number 12 looks like film. I don't know if some of you guys know what film is, but film was how we used to take pictures before we had digital cameras. My dad had a film camera. I used like some of the point and shoot ones that you'd like drop by the camera and you'd drop it off. I think I have like homecoming or prom pictures on that I took on the point and shoot digital camera. But anyways, number 12, this is mica. This is our biotite mica. There's two different types of mica. There's that we have in our class. There's biotite and there's muscovite. Biotite. The way to remember it is B biotite for black. Right, biotite mica. This one, it's very very thin. Right, you can see how it's almost like two dimensional. Like it's super super thin, almost like a razor blade. This one has that one plane of cleavage. It almost looks like pieces of paper. I don't want to mess up my sample, but sometimes you can actually peel it. Yeah, you can kind of see it kind of peels a little bit here. You can literally peel this mineral, and you can make like almost like fish flakes. You can peel off sheets of it. Yeah, so it has one really really good plane of cleavage. It's very strong this way, but the planes are weak this way, and so they peel off as a result. Kind of cool. Mica is another one of our silicate minerals. There's a couple different types of mica. In my class, we talk about biotite and we talk about muscovite. Me getting sent to the principal's office yet again for eating salt off the ground. You know, it's just it's just how it goes. Yeah, you don't want to. I wouldn't eat mica. I do believe I could be wrong, but I've heard they use mica in some cosmetics, like for like glitter. So they'll use like rock glitter in cosmetic products. All right. Number 13. Oh, this is a fun one. Number 13, another metallic one here. Kind of gray and dull. But the cool thing about this one, there's another very unique property here. Put our that there. We can literally write with this mineral. Hi, chat. All right, so it's a mineral that we can write with, and maybe you guys have figured out already what it is. But this is actually another element here. So this is pure carbon. This is the mineral graphite right here. It's kind of got this metallic-y, kind of smooth, kind of luster. But this is what we use in pencils. A lot of people think that we use lead in pencils. I don't think pencils ever used lead, based on what I remember from like reading about pencils a while ago. But I don't think pencils ever had lead in them. They called it lead, I think, because it looked like lead. But they've used graphite. So if you write, anytime you write with a pencil, right, that's gonna be graphite here. So this is pure carbon. Graphite is what we call a polymorph of carbon. There's different ways that carbon can be shown in the natural world. Graphite is one example, but you can also have carbon producing 4 bonds in 3 dimensions. Carbon is kind of unique. It wants to get 4 electrons, so it shares 4 electrons. But carbon makes diamonds, right? And so diamonds are the hardest mineral, hardest naturally occurring element, hardest naturally occurring thing, basically, on our hardness chart, which is kind of crazy, right? Because this is also carbon and it's super soft. Like you can write with this type of carbon, right? The reason for that is in this mineral we have the carbon molecules are arranged in 2-dimensional like sheets basically, and then they are loosely bonded to other carbon molecules in other sheets, and so the bonds are strong within the sheet like this, but they're weak in between them. So we call these van der Waals bonds or van der Waals forces here. So graphite, the carbon is basically, think of it like laid out in like 2 dimensions, whereas diamond, the carbon is arranged itself in 3 dimensions. If you take enough pressure and enough heat and enough time, you can actually convert graphite into diamond. That's how they make like artificial diamonds. They just take carbon and they crush it down and get it really hot, and you can make artificial. I don't. Yeah, I guess you can man-made. You can make man-made diamonds that way. I like to call them artificial because it's still the same element, but I feel like the diamond companies got their hooks and got their hooks in the definition of rocks and minerals. But that's graphite. It's a very very soft mineral. It rubs off on your fingers really easily. It's what you write with in your pencils. All right. Wouldn't a pencil with real lead be insanely heavy? I mean, it would have a lead core, and then mechanical pencils, right? The tip is very small, so I don't know how much weight it would add to a mechanical pencil. But yeah, lead is actually much more dense. Lead is one of the densest things, one of the densest naturally occurring elements out there. Whereas carbon is like number 6 on the periodic table. So yeah, it would be much. In terms of if you compare the amount of carbon versus the amount of lead, yeah, it would drastically increase the weight. There is a lot of wood, and in this case, my pencil's got a lot of metal around it already. And these are, I don't know, what is this, 0.5 millimeters of lead, of pencil lead in my pencil. So it wouldn't add a whole lot of weight, yeah. But lead is also extremely toxic, which is probably the bigger concern, right? Yeah. The Romans, they used lead pipes and stuff, which wasn't really too much of an issue. Lead pipes, yeah, you can get lead in the water, but eventually it oxidizes and forms a seal around it. But the Romans, they would use lead in their makeup and stuff, and they would put lead in their wine to sweeten it, which was actually much more of an issue. I think if I remember right, the lead in the wine would react to the sugars and the acids, and yeah, it would turn it into a toxic version of lead. Whereas lead pipes, not the best, but you can kind of work around it or deal with it, So yeah, lead has been known to be toxic for quite some time. So they actually made a smart choice when they started making pencils, and they decided not to put lead in them. All right. Yeah, my hands are a bit messy. All right. 14, number 14 here. This is another version of why did they gave us 2 versions of gypsum? All right. So this is very similar to number 9. Where's number 9 here? Number 9 is the alabaster version. Number 14, this is they call it the satin spar. I mean, it's all gypsum. I mean, it should be fairly soft. This one I almost call rock gypsum sometimes. But yeah, my fingernail, you can see that little white line there. My fingernail easily scratches it. So it is going to be softer than your fingernail still. And number 15, what's going on? Number 15 is also gypsum. Yeah, this is what I was talking about, though. This is kind of the more transparent, kind of translucent one that I like to show this one more in class than number 9 and number 14. This one kind of pops a bit more in my opinion, but this is the selenite version of gypsum. There's just more gypsum here. But it just kind of shows the different flavors, basically the different kind of combinations and colors that our minerals can come in. Again, your fingernail easily scratches this. I put a little scratch in this one here. But this one you can actually kind of see the cleavage planes on, so you can see how it's relatively flat right here, and it reflects the light back fairly well into our eyes. And so we have at least one good plane of cleavage on this one. So that's why I like to show the selenite version of gypsum, because it more easily shows the cleavage plane, which makes identification easier for the students, whereas there's not a nice flat surface here, really. And number 9, I don't think has anything either. Yeah, no. Relatively boring. So there's no nice cleavage surface here. All right. Those are all of our minerals. All right. If you guys have any questions at all, again, feel free to drop them into the chat here. My hands are messy. Real lead pencils make you doing math that much. Yeah, I mean, the lead's going to get in your brain. It's going to literal brain rot, right? And prevents you from doing math then as a result. By the way, I really like my mechanical pencil here. When you write with it, the core, this is from Japan, it's called the Kurotoga, but the core spins, and so it always has a point on it. When you push down, it rotates the lead a little bit. Oh, it's so nice. I'm not being sponsored by them, by the way. I wish I was, but you can get them on Amazon for $10, $8. The Kurotoga mechanical pencils. Plus, I love red. It's my favorite color. All right. So those are our minerals, and that was 45. Geez, that was 45 minutes right there. So let's move on to bigger and better. We have our box of rocks, literal box of rocks right here. I have not opened this at all, chat. So this is we're gonna see it for the first time. It is shrink wrapped here still. So This went with this. Put that down there. All right, let's open this up. See what we got. What is my favorite mineral from tonight? Man, they're all pretty. Let's go back and look at the box real quick. They're not the best samples, unfortunately. I mean, we bought a lot of them, for the students, and in terms of sample quality, what's the best sample quality? The mic is really nice. Oops, and I'm dropping stuff. Nice. All right. Ugh. In terms of sample quality, like the mica is really nice. Number 12 is really nice. The graphite works really well. The calcite, probably the calcite, I think, because you can see the cleavage and it had a really cool property. So I'll go with my favorite one out of all of these is the calcite. I'm unimpressed by the gypsum. The quartz is okay. This one's kind of crappy. This one, I don't know why they gave us 3 versions of gypsum. Like that just seems kind of random. Like, I could see 2, but I couldn't see 3. I would assume, like, okay, if you're going to give us 2 of something, give us like another feldspar, because there's a lot of different flavors, a lot of different varieties of feldspar out there. And so that would make sense to give us that. I don't know, again, 3 gypsum seems a little bit excessive, but hey, it's whatever. All right, let's move on here. Let's go back to the chat. What kind of black magic mechanical pencil are you using? This is, I don't know if you heard me, but it's called the Kuratoga. How do you spell that? Kurutoga. And so, yeah, it spins the lead when you write with it, and there's a little eraser under the cap here. Yeah, it's a nice little pencil. I use it for all my note taking from my life. I use it in D&D also, so. All right. What do we got here? Introductory rock collection here, folks. Introductory rocks here. We got igneous, we got sedimentary, we got metamorphic, we got them all. Okay. We got maybe 15 in here. Okay. Well, this is cute. Look at this. Investigating the rock cycle. Wow, look at this. This is cute. A little cartoon, a little picture that comes in it. That's neat. It kind of show, I mean, it doesn't do a great job, but it kind of shows in general, like, where the rocks come from, I guess, or where you can find them. The environments, essentially. Let's see here. Where did my pencil go? Where did my pencil? There it is. It's kind of cute. Got a little rock cycle up here. That's not how I would have drawn it. I don't like that down there. But that's nice. They got the symbols. That's neat. So, like, this is the symbol for limestone. It's like offset brick pattern right here. You guys can see that? Yeah, like an offset brick pattern. The dots are sandstone. This is mud. Yeah, they got shale. They got conglomerate, right? And then igneous is like triangles, kind of. Yeah, that's interesting. Sandstone are these little dots right here, and so when I teach historical geology, they have to draw kind of like a column of rocks, and so sandstone is one of the rocks, and so like halfway through the test, like everyone just starts like tapping their paper to make sandstone. It's rather funny because you can't talk, right? But like you got 30 students just like tapping the paper all at once, like it's a fun moment. Let's go back to chat here. Gypsum actually the most common mineral in the Earth's crust, according. Yeah, right. Is this going to be on the quiz? Of course, it's going to be on the quiz. What's in the intermediate box? Yeah, there's no plateaus. Unfortunately, we only have some mountains. It's kind of weird. Like they labeled glacier. Like, why did you didn't need to label that? Like, it's not like we're not talking about geographic features here. But whatever. This is kind of cute. Is there anything on the back? No, nothing. Ooh. Oh, man. Okay, this could have been better. I thought this was Bowen's reaction series at first. But I guess here's a little guide for identifying igneous rocks. Do we like this, chat? Is this good? Um... it's okay. It's okay. This isn't terrible. Um, Description: fragmental, frothy, glassy, fine, combination, coarse, or extremely coarse. It's okay. Here, I'll show you what I teach. Since we're looking at this chart, here, let's move this to the side, and we can lead into the igneous rocks with this. And so when I teach it, we talk about the composition, which they do have across the top. They have composition across the top, so we like that. Compo. I cannot spell for the life of me. My mother is a language art teacher, and it never rubbed off. And they do have texture on the other axis, so that's okay. Texture. All right. But for composition, we have felsic, we have intermediate, we have mafic, and we have ultramafic. Those are our four main compositions, essentially. And then for texture, see, they use like very simple, like I guess kind of like everyday words. We like to use those, which is great, but we also like to use kind of the more scientific ones. And so we have phaneritic, we have porphyritic. I should have got like a real piece of paper, but whatever. Aphanitic. We have vesicular, and we have glassy. Yeah, my handwriting is trash right now. Sorry. I'm kind of sitting in my chair at a weird angle. But then, and they kind of show it, but like they should like put like some lines and some boxes. I don't know. They don't need like these colors. This like 1990s like Microsoft Word art like gradient can go away. But if it's phaneritic and felsic, we call it granite. If it's phaneritic intermediate, we call that gabbro. No, I'm freaking out. We call that diorite. We call it mafic is gabbro. And then over here, this is peridotite. And then we can segment those into a nice little box. We'll come back to those. If it's aphanitic and felsic, we call it rhyolite. If it's intermediate and aphanitic, we call it andesite. Andesite was the name of one of my cats, but unfortunately she passed away in January, so rest in fossilization, andesite. And then over here we have basalt, and I put an extra line there because I'm an idiot. Basalt. If it's vesicular, we really only have two choices for that. It's either going to be pumice over here, or it's going to be scoria over here. And if it's glassy, it's only one choice. Obsidian kind of goes out this way and that way. But composition, this is composition is basically the chemistry. So this is going to be what it's made of. So this is the different elements. The felsic lavas and magmas get their name because they are rich in silica. So feldspar and silica, basically felsic. Mafic, they are rich in magnesium and iron. So magnesium is M. I didn't name these things, but these are going to be denser over here. Mafic typically is dense and dark. Felsic is typically less dense, lighter in color, and then intermediate's a mixture. Ultramafic will typically actually be green. And so if I had more room, I'd add that on, but like felsic is kind of white to pink. Mafic is mostly black with some green. Intermediate's kind of like gray or in the middle, 50-50. Then ultramafic tends to be more green. Texture, then, this is the crystal size, essentially, which is actually kind of nice, I guess, for this one. They do kind of show a little bit, like they show like little examples of the crystals. They don't really give you a good sense of scale, though. What a lot of students kind of struggle with igneous rocks is more texture more than anything. Just because, like, phaneritic means it has large crystals, but when I say large, like, I gotta put it like in quotation marks, because when I say large, we mean crystals that you can see with your eyes, basically, like they're large enough to see. Whereas aphanitic, you'll have crystals, but you can't see them with your eyes. You need a microscope to see them. Porphyritic is a mixture, so this is actually going to be like porphyritic rhyolite, we call it. This is porphyritic andesite. And this is porphyritic basalt here. So it's kind of a mixture. I think of like porphyritic being like chocolate chip cookies. So you'll have the big, large visible crystals, and then they'll be surrounded by areas where there are no crystals. So the crystals are like the chocolate chips. The ones that you can see are like the chocolate chips, and the crystals you can't see are like the dough. Vesicular is going to be like frothy and kind of foamy. So think of like a root beer float. You have your ice cream, you pour your root beer in, it foams up and it kind of sticks around. That's going to be like our pumice and scoria. Or like if you get a fountain drink, you go to Taco Bell, right? You get your fountain drink, all that foam when you're filling it up, right? That's going to be like your pumice or your scoria. And then if it's glassy, you only have one choice. It's got to be obsidian, regardless of color. So I mean, this is okay. I don't like the gradient here. Descriptions are okay. You probably don't really need these. I would add more to this. I like the appearance. What the heck is this on this side? Size? Oh, site. So it kind of tries to tell you where they are, I guess. Yeah. So these are extrusive up here. These are intrusive down here. So these rocks form inside the Earth. These rocks form close to or on the Earth's surface, which is then related to the cooling rate. Because in order to get big crystals, like in granite, in order to get these big crystals, it has to cool very slowly, all right? If you just take, like lava and you cool it off very, very quickly, that's how you get obsidian right here. So it has to cool very, very slowly to get the large crystals. So this is okay. They should hire me. I would improve it. We haven't even looked at any rocks yet. What's the next piece of paper that we have? Sedimentary rocks. So sedimentary rocks are like the most difficult of all the rocks to identify. There's a couple of reasons for that. There's a lot of different ways sedimentary rocks can form. Like igneous rocks, it has to be from like lava or magma. So you're starting off with something very similar. Where sedimentary rocks is like, yeah, you wanna start with like sand, cool, like it came from a rock. You want to start with things that were once alive, cool. You want to start with a chemical reaction, cool. And so sedimentary rocks kind of encompasses a lot of different kind of oddballs basically that are kind of thrown into this category. And so let's see here. They've attempted, what does this mean? Appearance. What is this? This is appearance and there's just circles? What the hell is that? It doesn't tell me anything. Lithification. Okay. That's kind of good. Additional clues. Earthy odor. Specimen. Okay, that's kind of right. Rock name. Okay, this is hot garbage. Oh God. Yeah, we'll tell the students not to use that one. Sedimentary rocks. Use some scrap paper. Is there scrap paper here? What is this? It's got my address on it. I don't trust you guys that much. Sedimentary rocks. I'm just going to keep using index cards to be consistent. The easiest way to identify sedimentary rocks is to ask a series of questions. And you ask yes-no questions. And then based on your answer, you either proceed one way or you proceed another, like a flow chart, basically. I don't think I want to write it all down because there's like 4 or 5 steps to it. But like the first thing is like, does it fizz? And if yes, then it's some sort of limestone. We saw a mineral that fizzes, right? We saw calcium carbonate that does fizz, right? And then if no, you go to the next step. Do you see pieces of rocks? If yes, then it's clastic, and we can investigate further. But like if no, then we ask another question. So we kind of use like process of elimination. This is how I teach it, but we use process of elimination to kind of identify our sedimentary rocks. But it's weird because like, okay, like okay, let's say you don't see pieces of rock and it doesn't fizz, right? It actually still, like question like 5 could have you looping around and coming back to clastic, because there are clastic rocks that you can't see the pieces in, but we're ruling out a lot of them but with question 2. So sedimentary rocks are by far the most difficult of all the rocks to identify. So this, I don't like this at all. The igneous rock one is better. Let's go to our last group. This one is pretty hard to mess this one up, I think. Metamorphic rocks. What do we got here? Parent rock. Yeah, so for metamorphic rocks, there's 2 main groups, right? We have the foliated ones and we have the non-foliated rocks. The foliated ones, these will have layers in them from heat and pressure squeezing them. It's what we call differential pressure. And so if the pressure comes in like this, if the rock is being squeezed like this, my pencil's actually in the right position. The mineral grains will align themselves 90 degrees to the pressure, perpendicular to the pressure. So if the rock is being squeezed this way, the mineral grains will align themselves this way. And so those are our foliated ones. They have the 4 that we need: slate, phyllite, schist, and gneiss. They put amphibolite on there. Okay. They put migmatite. Okay. It's just kind of weirdly drawn, but okay. Non-foliated. We've got marble, yeah. We got quartzite. We got anthracite. I feel like they're missing a few, but maybe that's all that's in the box. But this is probably the best out of the 3, but it's also the easiest to not mess up. So, all right. Now maybe we can actually look at the rocks here. Let's go back to chat here. I see Onion is just dominating this chat here. Frothy, yeah. So you can have pumice and obsidian are kind of almost like sponges. They kind of have that frothy texture. They called me Rhyolite Porphyry in college. That must have been your street name. Also, I must GN now. Oh, man. You show these shitty charts. I will show these shitty charts. Who's the boss? All right. But, all right, chat. Let's do our big reveal here with our box. We haven't opened this yet. We don't know what we're going to get here. So let's just see what we got. Ooh, okay. Initially, first impressions here, I do like how the samples are bigger. They were kind of small for the mineral one, but I do appreciate the increase in sample size here. I don't remember if this ended up costing more than the mineral one or not. There were 15 in the last one, yeah, and there's just 15 in this one, but the samples are just they're just bigger than they were. We'll start with the igneous rocks. So the first row here, they give us 5 igneous rocks here. This is a nice sample. I like this one quite a lot. It is nice and sharp and jagged here. You wouldn't want to push your thumb too hard against these edges right here. This one's a common one in like Minecraft and a lot of video games and stuff. But this is this is obsidian right here. Can lower our camera down, kind of zoom in a bit more again. This is obsidian right here. This is volcanic glass. This is lava or magma that cooled very, very, very quickly. It cools so quickly the minerals that were in the lava and magma didn't have time to arrange themselves into a crystalline lattice pattern, and so that gives us our black obsidian right here. Very nice sample too, good size, very sharp. Obsidian and glass have what we call conchoidal fracture, so I can see it. Hopefully you guys can see it if I angle it maybe just right. You can kind of maybe see there's like this kind of like circular, like kind of scooping pattern in here. And that's called conchoidal fracture, yeah. It literally looks like broken glass, kind of scooping pattern right here, yeah. And so that's a dead giveaway for obsidian. You'll see the conchoidal fracture. It's the only glassy rock that we have, and so it's relatively easy for the students to identify. Number 2 is a classic, beautiful sample here. We've got a variety of crystals, and we can see these crystals, right? So when I say large crystals, this is what I mean by large crystals, right? Maybe you're thinking of something, really, really big, right? But when we say like large crystals from our igneous chart, right? When we say phaneritic, this is what we mean. And so this is phaneritic, and it is light colored. This is going to be granite right here. Granite is one of our igneous rocks. We have some good crystals that we can see. There's a really nice large piece of feldspar. I don't know if you guys can see it right in here. We can see the cleavage plane of it. It catches my eye. You guys' viewpoint is a little bit different. Let's see if I can get it in chat. Yeah, right there. You can kind of see that this long crystal lighting up. This is one of our orthoclase feldspar crystals that we saw in the mineral box here. And so you can actually have different like flavors. You can have different types of granite based on the ingredients that are used to make it. So this is a pink granite, but you can also have one that is rich in other types of feldspar. Like we had orthoclase, you can have plagioclase feldspar, which usually makes more of like a white granite. Yeah, very, very nice. Granite is used, for a lot of ornamental and decorative things. A lot of people will get granite countertops for their kitchens, but the thing is, it has to be light colored and has to have large crystals for it to officially be granite. A lot of like salesmen, they'll call something granite when it really isn't granite. It's kind of like how your parents call everything Nintendo. No, mom, I'm playing Xbox, right? No, I'm on the PC. But no, yeah. So it's kind of like that. But this is our granite here. Number three. Number three, there's a little bit of crystals in there. Not the best sample, but overall, this is going to be basalts right here. I don't know if you guys saw the news recently. There was a geologist who went to jail. They were charged with basalt and battery. But this is basalt right here. Decent sample. The crystals are a little too big for my ideal liking, but hey, work with what you got. Basalt is our mafic rock, so you can see how it's mostly dark black in color, and it's lacking crystals, so it's down here on our little chart. Basalt makes up most of the oceanic crust, which is kind of cool. So most of the ocean floor is made of our basalt right here. Granite, going back to number two, granite makes up most of the continental crust, makes up most of the rocks that are make up the land. The reason we have oceans and the reason we have continents in the first place is because granite's density is a little bit less than basalt's, and so the granite sits higher up. Basically, it floats on the mantle better than the basalt does. Granite's 2.7 grams per centimeter, whereas basalt's closer to 3 grams per centimeter. So it's that little bit of difference. The granite basically just floats higher, and that gives us our land, and this gives us our deep oceans. If the Earth was all, one rock, well, then it would all be pretty level, and there would be water covering everything. Not as deep, right? But there'd be water everywhere. So it's a good thing that we have, these two different rocks that make up our different continental and oceanic crusts. We think that when the Earth first formed, actually, it was mostly all basalt. And then this basalt was melted and basically recycled, and some of it became granite that floated up a little bit higher, and that started to produce our continents. We see evidence of this in the geologic past. We see evidence that the continents had actually grown in size over time. So as we get more and more oceanic crust subducting, being melted, and being recycled, some of it gets converted over to granite, which floats up, accumulates, and sticks around as our continents. And so over time, the continents have actually grown and gotten bigger and bigger in size. Some of the oldest known rocks in the world are in the middle of Canada. So at one point, those rocks were, as a little island chain, but they've stuck around ever since then. So it's kind of cool. No one's talking in chat after Onion left. Oh well. All right. Number four. This is scoria right here. This is one of our vesicular rocks. In fact, you can see the little bubbles. You can see the frothy pockets all over this one, like our frozen foam right here. But this is volcanic scoria right here. It's relatively lightweight. It's made of the mafic stuff, so it's got iron, it's got magnesium in it. But if we had the light-colored version of it, which is called pumice, it can actually float on water. But this one's going to be too dense. But pumice is the only rock that can actually float, which is kind of cool, kind of fun. But not this one. This is scoria. This is the darker cousin of our pumice here, but still a very cool rock. You can often find this in decorative gardens and stuff. People will use it. I find a lot of scoria by railroad tracks and stuff. My parents have a bunch of scoria in their backyard that rolled downhill from the from the railroad tracks that aren't too far. So kind of neat, kind of cool. That's scoria. Number five. This is a rough one. This is rhyolite right here. It's kind of hard to even tell this is igneous, but this is a light-colored version, basically, of granite. So you can see how they're both light-colored, but you can see how this one, the granite, has the crystals, while the rhyolite, there is no sparkle, there is no shine, right? And so then, as a result, this is aphanitic, this is phaneritic here, right? Rhyolite, typically we can find it on continental volcanoes, so think like Mount St. Helens, think like volcanoes in Alaska and stuff. You can find them sometimes producing rhyolite. Yeah, it's one of our felsic, light-colored igneous rocks, right? Those are all of our igneous rocks. So the first row here is all igneous. We can then move on to our sedimentary rocks. This is number 6. Whoops. This is number 6 right here. This is shale, all right? Kind of the easy way to identify shale is you can see these thin little mud layers right here on the edges, on the sides. Very cool, very pretty. Shale, though, the way we get shale forming, shale comes from mud, all right? Mud and clay. And our most common mineral, if you guys recall, that is our feldspar. When that is chemically weathered, it will dissolve and break down. It has a chemical reaction called hydrolysis. It breaks down, and you can get feldspar turning into like clay and mud, like kaolinite is relatively common. And so shale is the most common rock because it comes from the most common mineral. That makes sense, right? Most common rock comes from the most common mineral. And so as a result, if you're ever out looking at rocks and you don't know what you're looking at, this is like picking C on the test, right? They say if you don't know the answer, always pick C. Yeah, so the same is true with this. If you're not sure what you're looking at, always guess shale because you have the highest percentage chance of being right. All right, but this is our shale here. Some shales will contain, I don't think we have any, but some shales will contain fossils. The mud deposits are very, very fine grained, and so they preserve fossils very, very well. It's almost like the grains, like the resolution. This is almost like a 4K or like an 8K, like fossil preservation rock right here. All right. Number 7 is a type of limestone here. It's called tufa. Typically found from like heated water, typically like geothermal, maybe water. You can find it sometimes. But it is a limestone, so we should be able to see if it fizzes. Yeah, so let's see here if we can get any bubbles. Oh yeah, maybe you guys can even see that. I pour the acid on and it just foams and it just froths like crazy. Here, I'll put it right here. Yeah, you can see it quickly absorbs it too. There's a lot of porosity and permeability here. But this is a type of limestone. There's a lot of different types of limestone. I I don't use tufa in my class. I use like fossiliferous limestone, or I use micrite or travertine. But either way, it's limestone. It gets the point across. It does show that fizz. It does show the connection there to calcite. Number 8. Ooh, this is not a bad sample actually. This one's kind of nice. This one we can see there is some striping, kind of like banding, kind of going on here. Hopefully, kind of picks. Yeah, you can kind of see that in the chat. Got this striping kind of banding pattern going on. This is one of my favorite rocks. This is quartz sandstone right here. There's different flavors, different types of sandstone. Quartz sandstone is the most common type of sandstone, and sandstones are the second most common type of rock after shale. So our mud, right, our feldspar makes our mud, makes our shale, while our quartz, which is the second most common mineral, makes our quartz sandstone, which is the second most common rock. You see a connection there? If you have a very, very pure quartz sandstone, they call it a quartz arenite. So rock that's near and dear to my heart. But quartz sandstone can make some very, very pretty colors. You can see there's like little stripes and bands here. Different impurities got into it at different times. So these might represent seasonal changes maybe, or different rocks weathering and breaking down. I'm not sure what would have caused them specifically, but you get different impurities, different agents that get in there and cause those striping and coloring. It feels like sandpaper, right? It's literally made of sand. Mine's also pretty sparkly. Hopefully that's being conveyed. I don't know if the camera can pick it up, but there's a lot of sparkles in here. All the little sand grains you can see as they kind of sparkle and glimmer in the light. Number 9, this is a pretty good one. 9, this is conglomerate. So conglomerate is another one of our clastic sedimentary rocks. Shale is made of small pieces, microscopic pieces of mud. Sandstone, you can see the sand grains. They're tiny, but you can see them. But now we've got a rock that's made of pieces that are much bigger than sand. So you can see these little pebbles. You can see these little boulders here in the rock. We have 2 rocks that are actually made of pebbles. There's conglomerate and there's breccia. Conglomerate will produce round pieces, while breccia will produce more kind of angular, jagged pieces. We don't see that here with this one. We see the nice round pieces. So this is going to be our conglomerate here. It's glued together by, I don't know what it's glued together by, but we have a variety of different things that can act as like cements. The most common cements are going to be like quartz. You can have calcite acting as a cement. You can have hematite acting as a cement. Calcite as a cement is very frustrating because you can have a rock that's, it's very clearly got these pebbles in it, and you think it's clastic, but then if you put acid on it, then it might fizz, and that throws students off sometimes because they think, oh, well, it fizzed, so it's got to be a limestone. Well, yeah, but look at it, you can see the big pebbles. It's not actually going to be a limestone. Calcite is just acting as the glue. Number 10, this is a kind of more basic looking limestone here, not as exciting as the tufa. I'm trying to see if we might have a little no, I don't think that's a fossil. I thought maybe this was a fossil. I think it's just how it broke. There are some interesting little inclusions in here. I don't know if those are fossils. They don't look like anything like a fossil I've seen. I'm not a paleontologist expert by any means, but they don't look like, they just look like a little crystal growth. They don't look like anything that was alive, really. No, but this is limestone, so let's see. Does it fizz? Does it fizz? Oh yeah, it's smoking. You can see the bubbles coming off of it. Yeah, so this is definitely one of our limestones here. Again, a lot of animals will use their seashells. They'll extract calcium and carbonate from the water. They'll make their shells out of limestone. And then when they die, they pile up and they can accumulate, and their bodies can turn into different types of limestone. Coquina is a type of limestone that's made of all kinds of shells. This is more of our classic kind of traditional looking limestone, but you can have different flavors, again, different types of limestone. And what's even kind of crazier is you can have limestone that forms through organic and then inorganic means, and that means it gets sorted into different sedimentary rock categories, which is very, very frustrating slash amusing when trying to teach sedimentary rocks. Like, oh, it's a limestone, so it's got to be bioclastic. Well, actually, it formed through a chemical reaction in the seawater, so it does throw the students off sometimes. All right, but we have our igneous, we have our sedimentary, and then we have one last group to go. We have our metamorphic rocks here. All right, number 11. This is a really nice one. This is slate right here. Slate is one of our foliated metamorphic rocks, so we can see the layering, right? We can see the patterning. If we turn it on its side, we can clearly see there are some really great layers that are developed in this slate right here. Slate, the parent rock for slate is shale, and if you look at them, yeah, they do look pretty similar, especially on their sides, right? But basically, you take a shale, you heat it up, and you compress it, and you make it into a harder, stiffer, firmer rock, which is going to be slate. Slate is used to make like chalkboards. So if you've ever written on a chalkboard, chalk is actually basically a type of limestone. So if you've ever written on a chalkboard with chalk, you're writing rock on rock essentially, right? That's a slate. Slate is often used too for like pool tables. So if your friend asks you to move their pool table, maybe you decline. It's probably gonna be very heavy because it's probably got a rock in there. Slate is often used for like decorative, like pavers or for roof tiles sometimes too. 12 is marble. Look at that. Hopefully you guys can see the sparkles in here. Very pretty, very nice looking white rock. Marble should be the only metamorphic rock that fizzes. Let's see if ours fizzes. Oh yeah, it's kind of hard for you guys to see. It's kind of white on white, but it is very bubbly. It is very foamy. It is very frothy looking. Yeah, so marble also reacts. So that gives you kind of a hint then as to what it came from. Well, right? Calcite fizzed, right? And limestone has calcite in it. And then marble also fizzes, and the parent rock of marble is going to be our limestone. So you take a limestone, you heat it up, you add pressure, and you can produce a marble. Marble's used again a lot of decorative uses. It's used, for making floors, for statues. The Washington Monument is made of like 3 or 4 different types of marble. I know it seems kind of crazy, but they were working on the Washington Monument, and the government ran out of money. Could you believe that? The government running out of money? No. Never. And so when they restarted again, they had a different type of marble, and then I think that was too expensive, so they switched to a third type of marble. So if you're ever in Washington, D.C., the Washington Monument has different types of, different layers, different colors of marble, basically, in it from when they stopped and started on the work. But this is non-foliated. I forgot to mention that. So there is no layering, there is no patterning, so it looks almost crystalline, right? You can see the random kind of assortment of crystals, whereas this one on the side, right, you can see the layering, you can see the pattern of the number 11. 13 is quartzite. It's kind of tricky when you look at that, but when you look at the side, you can see how it's all this fused together sand grains. Another non-foliated rock here. Quartzite is the hardest known rock. Not the hardest known thing, but the hardest known rock. But it comes from our quartz sandstone, number 8. When we add heat and we add pressure, we can squeeze it together and we can make quartzite, making the hardest known rock. This should easily scratch glass too. Yeah, quartzite. Quartzite can often look like marble, but quartzite will scratch the glass and marble will not, and then marble will fizz and quartzite will not. So these can come in a variety of different colors, so you want to test them for their chemical properties. 14, this is a great one. 14 is nice. It's written as like Gneiss, but it's pronounced nice, like have a nice day or You look nice today, all right? But this is nice right here. This is another one of our foliated rocks, right? You can see the layering. You can see the patterning going on here, the different stripes. To me, it kind of looks like a zebra cone that you might get like from the zoo or the museum where they mix the chocolate and vanilla kind of together. But we can see different minerals. The black is typically going to be like our biotite mica, whereas the white's typically going to be more like our feldspar or our quartz, depending on what we got. You can see these different stripes though, right? The minerals are aligning themselves. Oops, there's my pencil. The minerals are aligning themselves this way, and so the rock was squeezed then like this. It was squeezed this way, and the minerals grew perpendicular to the pressure. So these are kind of cool because they can, if we find them in the field, we can figure out which way the pressure came from, 100 million, 200 million, or even billions of years ago to form those rocks. Let me get my pencil. And we got one more rock, and they saved the punniest rock for last. Number 15. This is a piece of schist right here. I said schist. I didn't say anything else, right? This is not the best sample of schist, honestly. Not the best piece of schist I've ever seen here. But this is going to be one of our... Ideally, it's foliated. It's kind of hard to see it. There is some of this kind of schisty texture right here that we're seeing. But, yeah, not the best sample of schist, unfortunately. But this one is going to be foliated again, so we do see the layer and we do see the patterning. In terms of heat and pressure, we'll often start off with a slate. So we start off with like 11. As we squeeze it, we can get like, there's another rock in between we don't have in the box. It's called phyllite. It would go right here. And if we add more heat and pressure, then we can get gneiss forming then. So as you add heat and pressure, you can kind of see how the crystals, you can't see them, you can see them, and now they're even bigger, right? And they've got stripes in them now, right? So you can kind of see how the heat and pressure changes the rock, which again tells us about the history of the area. If we find a slate, okay, there was a little bit of heat and pressure, versus if we find a gneiss, oh wow, there was a lot of heat and pressure that hit this area. Okay, those are all. I put these back in the wrong order, but those are all of our rocks. That's everything that came in the box, guys. So I thank you guys for coming out, listening, and learning today. And I will probably repost this video elsewhere. So if you really are a sucker for punishment, you can watch it again, enjoy it again. Okay. Hope you guys had fun. Put these not the best charts. Put these back, and yeah, maybe we can do this again another time. All right. Have a good night.